We know from early in the year that we have three big kinematics equations to represent our linear kinematics. So we have delta x equals v naught t plus 1/2 at squared. We have v equals v naught plus at, and we have v squared equals v naught squared plus 2 times a times delta x. And we could solve most of our kinematics equations from those three big equations. In terms of rotational kinematics, we have three very similar equations. We have delta theta equals omega naught t plus 1/2 alpha t squared. We have omega equals omega naught plus alpha t. We have omega squared equals omega naught squared plus 2 times alpha times delta theta. So you'll notice that our equations are pretty much the same. The only difference is that now in the first set of equations we had delta x, we had v, and we had a. So delta x is our linear displacement. We have v as our linear velocity. And we have a is our linear acceleration. While with our rotational kinematics, instead of delta x, we have delta theta, which is our angular displacement. We have omega, which is our angular velocity. And then we have alpha, which is our angular acceleration. So essentially it's the same three equations for our rotational kinematics as we had with our linear kinematics. You just have to think about the different variables, and then also you have to think about the difference in the units as well. While with our linear kinematics everything was in terms of meters, meters per second squared, with our rotational kinematics all the units are in terms of radians, radians per second, and radians per second squared.